Alright, this is frictional forces on screws. So, screws are often used to transmit power or motion from one part of the machine to another. So, screws are often used to transmit power from one part of the machine to another. So let's say we had a square threaded screw. We could model it as a cylinder which has an inclined square ridge wrapped around it. So this is point B, this is point A, the radius is R. So if we were to take this inclined square ridge and flatten it out, we would go from A to B, where this height from the bottom of A to the top of B is called L. This is considered 2 pi r, since it's the circumference. And then this angle right here is considered theta, such that we can find theta by the inverse tangent of opposite L over adjacent 2 pi r. So L is considered the lead of the screw, or in other words, it's the distance the screw advances when it turns 1 revolution. And R is equal to the mean radius of the thread. All right. So we have a few different scenarios for a screw. The first one being upward impending motion. Which I have found to be a fancy way of saying tightening the screw. So, if you were to look at just a portion of this, like a little block, you would have your torsional moment divided by your mean radius of the thread. You would have your downward force, W. You would have a normal force and a frictional force opposing this. And the resultant of those two are and we've already found that this angle right here is considered phi s. And this n with the vertical is going to be theta. So let's write out that m is equal to the torsional moment. If we were to sum the forces in the x direction, we would get m over r minus r times the sine of phi s plus theta. And that's all equal to 0. If we did the same thing in the y direction, we would get minus w plus r cosine of theta plus bs. So if we put r equal to w over cosine of theta plus bs, we would get 0 is equal to m over r minus r times, r would be substituted in for w over cosine of theta plus bs times the sine of theta plus bs, such that m over r would be equal to w times the tangent of theta plus bs. Multiply both sides by r, we get that the torsional moment would be equal to r w times the tangent of theta plus bs. Alright, so that is the formula you use if it's an upward impending motion, aka tightening the screw. So another thing is a self-locking screw. And what this means is it remains in place under any axial load, aka W, when M is removed. So a screw is self-locking if phi s is greater than theta. And then if theta is equal to phi s, then R will balance W, and the screw will be on the verge of winding downward. So our next scenario is downward impending motion. When theta is greater than phi s. So we just learned that if phi s is greater than theta, it's self-locking, and the screw's not going to move if you take off the torsional moment. In this case, if theta is greater than phi s, it's not self-locking, and you actually have to apply a moment to prevent the screw from locking. So if screw is not self-locking, it is necessary to apply M, I'm going to call it M prime, to prevent the screw from unwinding. And in that case, M prime is equal to RW tangent of theta minus BS. Okay? And then our last scenario is downward impending motion where Vs is greater than theta. Or, as I like to call this scenario, you are loosening the screw. So we're going to call this M double prime, and that's equal to RW tangent of Vs minus theta. So if the screw is self-locking, which it is, Vs greater than theta, M double prime must be applied to the screw in the opposite direction to wind the screw downward. So if you look at this from the equations and from real life, this kind of makes sense, right? So if you had a screw that was self-locking, when you're tightening it, it takes a lot of force or moment to get it to get to the right load, right? But when you're unwinding it, it's a lot easier. So these two equations for upward impending motion and downward are very similar, except that you have theta plus Vs when you're tightening the screw, and Vs minus theta when you're loosening the screw. So that change makes it easier to loosen the screw rather than tighten it. The other thing about this, if the problem says that the screw is already moving, that means that you're going to use phi k instead of phi s, and that's the only difference. But of course it's a constant motion because this is statics. Alright, that's it.